All right, so this uh, session will start off with the overall architecture of TinyDB, and then, as promised last time, we'll cover Calcite and things like that. So, so overall, this is like the flow of our database. We have a command line interface class which accepts SQL queries, and then it passes on to query engine. So query engine talks to the parser for converting the SQL statements to a data object. Once the data object is ready, we'll pass it on to the query optimizer within the query engine, and then uh, the query plan or the plan overall will be talking to the storage engine via scans and then like retrieving the record. So this is like the overall high level flow of this database. And as we have seen in the previous video, we have a basic query engine which uh, initializes both query planner and update planner into basic planner. So basic planner is like an abstraction for both the query and update planner, and it also talks to parser, which is like the front end component to get the SQL converted to the data object. So after that, uh, we call the corresponding planner, and when you call the planner, it initially starts off with the table plan, and then it goes to the select plan and then the project plan. So I'm just talking about select plan alone, not the select with index plan. So yeah, as you can see, we start with this table plan, and table plan internally has got this heap record scan, read write heap record scan. So heap record scan is a component which is part of storage engine. So this is the point where you are interfacing with the storage engine, and select plan talks to select scan, which is like the one that has got the predicate condition for filtering out the rows, and then project plan has got the project scan, which is basically used for filtering out the columns. So this is like the overall flow of a query engine. And I think at this point we'll see how a Calcite query engine works. So on a high level, we have something called as Calcite enumerator, which is just a moment. Alright, so for the Calcite planner, what we do is uh, basically we want to create something called as Calcite enumerator. So that's like the starting point for the Calcite flow. So Calcite enumerator gives you uh, an iterator. Just a moment. Alright, so coming back, basically we start with the Calcite enumerator. Enumerator, as the name says, it's more of like an iterator pattern. So using both the catalog and the record scan, we create some sort of an enumerator so that Calcite can iterate over the records and fetch the records and things like that. So on a high level, this Calcite enumerator is the starting point for our Calcite flow. Then we go to Calcite table, which has got in this enumerator creation function as well as a function to fetch the field types for that particular table. And then we go on to the Calcite schema, creating a Calcite schema, which is kind of a proxy schema that we'll be using it to replace the JDBC schema. So up until I think these three classes are the main classes for Calcite enumeration, and in the so for this particular project I have just considered only the query planner, if I wanted to use update planner as well, I would need to implement another class, which I haven't done. But yeah, like the query planner gives you a idea of how to use Calcite along with the custom storage engine, so that shouldn't be a problem. So we start off with Calcite enumerator, then we use that to create a Calcite table, and then we use Calcite table to create a Calcite schema. Once you have the Calcite schema, what you do is you go on with regular JDBC connection. So I think when you create a JDBC schema, you are using the Calcite connection driver or something to create a mock JDBC schema, and you add a new schema, which is Calcite JDBC schema proxy, to the existing schema, and from there on you use the JDBC query on the schema to fetch the results and display the output. So like from there on, this the bottom four layers are basically the regular JDBC flow, I would say. So now let's see the code part of this. uh, all right, let's go with the query part. So yeah, so basically query engine, previously discussed, we have to query and to update, and then let's go with Calcite query engine. So as you can see here, so first of all, what we do is we initialize metadata manager. This was previously there for the basic planner as well. One thing that we do a little different is we add the Calcite DBC driver, which is, as I told you, it's generally we would use a MySQL or a Postgres driver, but then a JDBC driver. But in our case, we are using Calcite driver, which is kind of a proxy driver, and we set the properties for like lex of Java. So basically, I think it's kind of, I'm not sure what it is, but yeah, I'm assuming that it's setting the lexical analyzer as Java or something, and maybe to mean that it's for the JDBC connection or something. And then finally, what we do is we create a connection using the JDBC Calcite thing. All right, so let's go to the do query functionality. So basically what we do is we get the table layout from the metadata manager. I think metadata manager is something that we are yet to cover. All right, so I'll cover that soon. I think I just used I just focused on implementation, which is basic implementation of query engine, which is just basic and Calcite based. I'll go to the metadata manager soon. All right, so for now, let's assume that metadata manager is like a API which gives you the table layout for that particular table that you are doing the query. So you get the table layout, you get the list of SQL types. So what we are doing here is basically you are iterating through the table layout and then calling the fields. So table layout will give you the physical layout, and then schema will give you the list of fields and things like that. So with the list of fields, you are looking through that, and then you are calling the data type rules dot lookup. I'll go on to that as well, but then essentially what you're doing is you're uh, converting your data types to the Calcite data types. Now you have the field types. So after this, what you do is basically you create a table. So B is just like as I told you, it's just for ordering the classes. So basically this is the order A for like we start off with an enumerator, then that is used in the table, then table is used in the schema, and then like Java SQL type to Calcite SQL type, that's basically used to convert the Java SQL types to the Calcite data type. So that's nothing that important, but yeah, Calcite test is just for doing the primary test cases and things like that. So at this point, for the table to be created, you have the table name, you have the field types, and then you have the metadata manager details and things like that. So like you can create the table by using all the above details, and when the table is created, you create a schema by passing the table name as a single list table. So I think what you are doing here is like you are creating a single map. You're creating a map with just a single entry. You can have multiple tables as well, but then for simplicity I've just used one table. So you are creating a singleton map with the table name and the corresponding calcite table that we just created here, and then passing on to the calcite schema. So now we have a schema with just one table, which was just declared here. So at this point, what we do is we create a proxy. Okay, so what we do is we call this connection.unwrap, and I think this unwraps, and now what. All right, so as I was telling, basically this part creates a connection, like unwraps a connection, and then basically we now add our schema to this root schema. So what we do is we unwrap the connection, we capture what is the root schema within the calcite connection, and then we add our custom schema to this custom proxy schema to this root schema. So now from here on we can like execute the plain JDBC queries and then fetch the result set. So what we do is we use the general syntax for JDBC, which create statement, and then we execute the query. We get the list of columns. I guess. Sorry. The table layout will give you the list of column names, and then basically what we do is we iterate over the result set, and then uh, read the column value for each of the fields. So finally we close the result set and then close the state and transaction and return the table detail. Alright, so that is like on a high level how the query part works. Let's look into the enumerator. So here you can see that enumerator is returning an array of objects. So I guess array of object in this sense is the row. So row is, if you look at a row, it's just an array of column values for that particular row. So here you can see that enumerator has the generic parameters set as object array, and then we are using record scan and then physical layout for this particular thing. So in the enumerator, we initialize the scan to be heap read write record scan, and then in the current function what we do is we iterate through the fields and then get the value for that field. So in for each of the field we get the value corresponding value by calling the get value function. So we pass in the field name, we get the value at that value for that field name, and if it is an int, we convert, I guess, attribute to now. Alright, so if it's a integer value, we use it as an integer value. If it's not an integer value, we use it as a string value. So in our database, basically, we support only integer and string. So that's a basic rule that we can use. And then finally, convert the list of objects to an array. So the current is basically returning you the row, and then move to next is calling the next function within the scan, and then reset is resetting the scan position, scan iterator point to the beginning of the query start, and then finally we close in the close we close the scan. So this is like the overall enumerator which is implemented for the calcite, and let's see how table is done. So on the bottom part we have this abstract enumerable. So we have overridden the scan in this um, thing. So for the calcite table, what we do is we extend an abstract table and implement scannable table. So abstract table will give you, like, I think it's kind of a template pattern that we are using here. So abstract table will give you all the template related functionalities, and then scannable table will give you the query planner capabilities on the table. So right now, the table is only queryable, but then if you want to make it updatable, so if you want to modify the table, then you have to implement the modifiable table, and that will have few other functions to override. So I'm focusing only on the scannable table so that it's just simpler. So as you can see, we are overriding a scan, and we are basically creating an abstract enumerable, which is another which is like overriding, sorry, which is having an enumerator. So this is our enumerator that we have just seen now. All right. So for the get row type, what we are doing is this is kind of a singleton pattern. So if the row type is null, then we initialize the row type, else we reuse the row type. So we go over the list of field names. So like I think field names is already passed when we create the table. Let's see here. So here you can see that the field names are passed. So with the field names, what we do is we uh, yeah. So what we are doing is basically we are fetching the field types for that particular index, and now we have field name and the field type. So field type in our case, uh, okay. So here's the thing. All right. So field type in our case is JDBC field type. All right. So in the field types we are using SQL types, and this is coming. Oh, just a second. I, mm, all right. I think I got the thing. So what we all right. So here's the thing. All right. So I think there was a small correction. So when we create this table, right, we are passing in the field types, and if you see this field type, what it does is from the table layout we get the fields, right? We loop through the fields and we convert the fields to the corresponding type, right? So at this point we'll get what is the type of the field. So in our case, the storage engine saves the type of fields as Java SQL type. So if it's a bit, we have -1. So in our case, we are just using integer and varchar. So I think for the varchar, it's value 12, and for the integer, it's going to be value 4. All right. So uh, coming back, we convert the so we loop through the fields, we fetch the corresponding SQL fields which we use in the storage engine. Now what we do is we convert those fields to calcite fields, right? So what we do is we call the lookup function. So in the there is this class called Java SQL type to calcite SQL type conversion rules. So it's a singleton class where we have a hash map. Uh, yeah, it's a singleton class where we have a hash map. It's just an immutable map containing the corresponding uh, types, SQL types, and the corresponding calcite types. So for the integer SQL type, we are mapping it to the SQL calcite integer type, and then for the varchar, we are converting it to varchar calcite type. So, and I think this instance, yeah, we don't need this instance, I guess. Yeah, okay. So we are actually calling the instance for just fetching the map. So I think this is just a singleton class which is just having an immutable map, and then the function of lookup is just searching the corresponding key or value associated with that map. So as the name suggests, it just converts SQL type to the calcite type based on the key value that's entered in here. All right. So at this point, so you can now see that we have field name as well as field type, which is the calcite field type for that particular field name. All right. So now what we do is we create a field. Right. So this time we use the field name and the field type as the index for that field type. So once you create a field, you add it to the list of fields. All right. So we have list of fields the same size as the field names array, field names list. And then finally, what we do is we set the root type as I think this is just the syntax of it. So basically, we pass in the list of fields, the list of calcite fields that we have just calculated, and then we create this relation record type. Once you have that record type initialized, you'll use that continuously in the. You will not be creating a new record type again. You will be just reusing this thing. All right. So on a high level, we have seen how table is created. So basically, we just need to modify to override two functionalities. One is get record type, and the other is scan. Right. Now we'll go into the schema. So we extend an abstract schema, as I told you, abstract table, abstract schema, all these things are basically template patterns, maybe. So they have the functionalities inside of it. We'll be just overriding the thing that we want to modify. So the calcite schema accepts a table map. So table map, as I told you, in here, it is just a singleton map in our case, which has the table name and the corresponding calcite table. Right, so and then finally, this is the only function that we are overriding by get table maps. We return the same table map that we initialize in the constructor, and we have already covered this conversion rule. So yeah, I think this is another test class which you can use to just validate the calcite functionality. So as I was just saying, we start off with the table layout, we get the corresponding list of SQL types, and then we create a table, we create a schema, we modify we create a JDBC connection, we unwrap the JDBC connection, we extract the root schema, we add the proxy schema to the proxy calcite schema to the root schema, and from there on we can execute the JDBC query as such and then work out the results. All right. So, yeah, that's pretty much about the calcite thing, I think. Yeah. So, all right. So just going back to what we have just seen, we start off with a calcite enumerator, which creates all the which creates an iterator pattern. So calcite enumerator has access to both catalog, and catalog also talks to heap record scan, as well as it also uses the heap record scan dot next functionality to get the next record. So this is kind of the interface. Heap record scan is the interface which talks to the storage engine. Right. From calcite enumerator, we go to Calcite table, which overrides two functions. One is the table scan function, and the other is the row type function. Then we have the Calcite schema, which just adds a proxy, which just adds the corresponding table and the table name into the schema. And from there on, this dotted line just means that from there on, the things are pretty different. What we do is we create a JDBC schema, we add the proxy schema to that schema, and then do the JDBC SQL query using JDBC APIs, and then finally read the result set. All right. So that's pretty much about the Calcite, and we'll now go into the catalog part. All right. So table DTO is just a DTO which will be used in the CLI driver for printing out the table properly. So we have the column names, corresponding row values. It's just a 2D 2D list of lists, and then a message is just a in case of a if it's not a query DTO, then you have message containing the corresponding uh, so message will contain the update messages and things like that. All right, so now we'll go to the metadata manager. I think metadata manager is the metadata manager and or catalog manager and heap record scan are the two things that we need for the Calcite to work. So if we have that sorted, then I think half of the things are sorted for using query optimizer as Calcite. Right. So we start off with the metadata manager. We have table manager, index manager, and stat manager. So I think this class is basically just calling the correct corresponding functionalities for table manager and index manager and things like that. So I'll go over to the one second. They just made a small correction here. So basically, in the I just moved the stats manager here because I think metadata manager is talking to the three managers, which is index manager, table manager, and stats manager. Uh, I think it would be better that we keep it here. All right. So and in the basic query plan or basic query engine, we have just the query optimizer and the SQL scans. So that's fine. Okay. So let's start out with the table manager. So table manager is uh, is kind of the catalog which stores table information. All right. Uh, so here we are creating two table definitions. All right. So one is called table name. Uh, sorry, table catalog, and then this is called. Okay. So one is called table catalog, and the other is called field catalog. You can say this as a table which contains table name and the corresponding slot size, and then this is another table which contains the table name, field name, type, length, and offset. So we have the table name here, we have the corresponding column name or field name, and what is the type of that column name or field name, what is the length of the column name or field name, and then corresponding offset. So when you create a new table manager, if we are creating it for the first time, like I think is new is past when I think let me go back. So if you see um, basic query engine to query, where is it past? All right, so here's the thing. So basically, in the metadata, when you initialize the metadata manager, we are calling the file manager isNew. So the file manager has this isNew functionality, which determines if the particular file folder, which is in our case TinyDB, was created or not. If it's not, if it's the first time that you're creating it, then it initializes both this catalog tables. So we have the TinyDB columns table and then TinyDB tables table. So here we check whether the directory exists or not. If it doesn't exist, basically we create these two things. So that's how the isNew is getting passed over. All right. So where were we? Okay, so if you're new, then what you do is you use the create table functionality to create tiny table tables and tiny table columns with the corresponding definition. All right, so now what we do is we go to the create table function. Okay, so in the create table, we create a physical table, physical layout, and then we use heap record scan to correspond, like to go to the seek to the insert position, insert beginning, and then we set the corresponding uh, strings, uh, like corresponding table name and the corresponding slot size based on this, uh, based on the function that's provided by the record scan. All right, so uh, at this point, since this is like tiny table tables is considered as a table, we have to add it to both tables as well as columns, right? So it creates a table having the specified name and the corresponding schema. So once you created the tiny table tables, now you have to create the corresponding columns. So we seek to the insert beginning. We start by adding the table name. We go to the field name, type, length, and offset. So we'll go over the schema. Like basically, schema just gives you what is the corresponding type of the field. So as I told you, this will return the SQL type. I think I'll go over it once, but not now. All right. And then schema.length will determine what is the length of this particular thing. So I think I'll go over it later. And offset. All right. So let's take it on a high level. All right. So we have the heap record scan creating a table, and then we have the heap record scan creating the tiny table, tiny DB columns. Okay, so we have created the table now. Now, whenever like say for example any query optimizer like Calcite or a basic query optimizer wants to alright, so we were covering this get layout function. So we pass in the table name and the transaction object. So what we do here is we start off with the table record heap read write record scan. So we pass in the table name so that the scan is on that particular table file. And so if you see the table is like the file layout would comprise of multiple blocks, and each block will have a couple of records. All right, so let's so the heap read write record scan is basically an iterator over the records, and you will get one record at a time. Okay, so I think that's going to be covered in the storage engine, but on a high level, it's just fetching one record at a time. So here you can see that this will be the layout for the tiny DB tables. We have table name and the corresponding slot size, table one name and the corresponding slot size, table 2 name, corresponding slot size, and things like that. So what we do is we iterate over all the tables one by one, iterate over all the records one by one, and then find out which is the table name that matches with the corresponding table name. Once you get the match, you use the corresponding slot size, and that is recorded, that's captured after the while loop. Similarly, we will use the catalog table or the columns table. Sorry, not the catalog table, the columns table. And in the case of columns table, we have the same layout. Basically, we iterate through the whole records and find out which is the table which contains the corresponding table name and what are the field values associated with that record. So here we can see that the table name one is having a field name say A, and this is having a field name B, and then type in this case A was of type int and then B was of type varchar. uh, the length was 9 for this, and or 9 into the character size of one character, and then in this case integer was like 4 bytes or say, let's say. And then offset, I guess offset is going to be the offset within the or the index version within the record. So I think table name is going to occupy a particular set of size. So let's say table name, the maximum size is 20 bytes, and for the table column name, the maximum size is 5 bytes, and then integer is going to take up 1 byte. So we have total 26 now, and then after that 26 plus 4, 30, and then in this case the offset, oh boy, sorry, that's wrong. All right, so here's the thing. I think we'll cover the offset a little bit later as well. So what I think is offset is going to be what is the position or the starting position within the record. So if the record contains multiple columns, say A and B, then on a high level offset would be like for A it would be 0 and for B it would be 1. Okay. So that's like a high level overview of offset. So what we do is we loop through all the items, all the records within the table TinyDB columns, and then we capture the table name. We check if the table name is equal, and if it's so, then we add that to the schema. All right. So finally, we create the schema. We capture the size. Voila. We create the table physical layout. Okay. So that's about the table manager. Table definition. I think in this case, let me just go back. I think too many tabs are open. Let me go back to this. Okay, so here you can see that schema is actually the table definition. So let's go to this table definition. So we have fields and information about the fields. Okay, so all the field names goes with this add field uh, function where you specify the field name, the type, and the length. Okay, so length is an attribute which is applicable for varchar, and then type in this case would be the one that's defined in the SQL types, which is varchar or int. Okay, so basically you put the field name and the corresponding field info. So in the field info we have the type and the corresponding length. As a like field info is just a wrapper around that. Add integer field. So yeah, so this is just a function. Maybe you can call it as a set function, which passes the integer as the type, and then length is 0. As I told you, length is not a relevant thing for this thing. And in the case of add string field, we have the corresponding varchar, which is, I guess it should be the SQL type. Yeah, it's the this is java.sql type, and then we have the length, which is already passed from the user. And then we have add function, which kind of uh, adds a field. All right, so yeah, I add a field to the schema having the same type. All right, so I think I don't think we are using it. We are using it. Well, okay. All right. So we use it to. Okay. So basically, what we do is we use it to create a new schema out of it. So, yeah, I think arrow could have been used, but then never mind. I think we may not worry about that. So what we are doing here is I think add a field to the schema having the same type and length and corresponding field analysis. I think we can skip this for now. So fields will return the fields and then hash field will check whether the field name is available in the schema or not, and type will return the corresponding type, which is so you get with this part you get the field info and then the type will give you the corresponding SQL type, and finally I guess length will give you the length of the table if it's a length of the column if it's a varchar or not if it's varchar. All right, so we have covered table definition. Now we'll go to the table physical layout. So table physical layout is just an abstraction for the schema as well as the offsets. Okay, so we have the schema that we previously defined, and we have a map which captures the offsets. Okay, so once you create a table layout, basically what it does is it starts off with the like starts off by setting one byte for the beginning of the block or beginning of the record. So I think that byte is used for capturing information like whether it's empty or not. So if when you delete a record, you basically toggle the bit to zero so that any other record which fits in that position can occupy that position. But yeah, or also like when you set the bit to zero, you can basically once you done the when once you run the compaction or defragmentation, you can remove all those entries in one shot. Okay, so you first leave a space for the bytes, then you iterate over all the fields. So in the fields, basically we start by yeah. So we start off with the first field having the position after one byte. So yeah, I think we will start with the so in use will have one byte. All right, then we have field one, which will have like the position after it. So on one byte, you can say in use will have field one will have one byte as the starting point, and then length in bytes would be used to calculate the byte of the next field. So A would have this thing, and B would say, for example, have 3 byte as a starting index. Uh, okay, so I think it should have 5 because let's assume that A has that integer type, and then we'll see what length in bytes value for the integer type is. But then, yeah, we start off with in use, then we have A and B. So A will have 1 byte, and then B will have 5 bytes as the offset. Okay. In use will have 0 byte because it's the starting thing. A will have 1 byte because in use took 1 byte. B will have 5 bytes because A might take 4 bytes. So previously A's starting position was 1. When we add 4 bytes for A, then we have like 1 plus 4, which is 5. So 5 would be the starting offset for B. So now let's go on to the length. So here's the thing. We start off by capturing the schema definition information. We check what is the field type. If the field type is integer, then we so if the field type is integer, we are only putting 1 byte. I think. Okay, that's weird. But okay, I think 32 by 8. Oh, sorry, 32 by 8. It's 4. So yeah, right. Uh, Oh, right. So what we are doing here is actually we are capturing what is the integers byte size using this function. So I think this is defined in the Java class itself. So integer dot bytes will return 4 because uh, integers in Java is like 4, at least 4. I think I have heard that it's dependent upon the operating system, but yeah, let's assume that it's 4 for now. And for the uh, for the variable, I think I I hope I'm still audible. Mm, seems like my audio got cut, but yeah, one of the earphones are working. So, uh, okay. So in our case, hello, uh, just a moment. Okay. So in our case, basically we are using the function within the page. I think I don't know. I shouldn't have put this function here, but then yeah. What we are doing is we are capturing what is the maximum size for that varchar field. So we pass in the field name, and I think we get the corresponding. Say for example, if it's varchar of care of 9, then we get the corresponding 9 value, and we check what is the maximum size bytes required for a string to have the length of 9. So here what we are doing is we check what is the bytes per character. So I think char set dot new encoder dot max bytes per character returns what's the bytes per character required, and then we are essentially multiplying the string length with the byte character, and then I think 1 byte is uh, separated out. We Oh, yeah, right. So when we are encoding, I guess we'll be putting the length of the character, varchar character, and then the length of then the entire payload. So first byte is the one that we see. Okay, it happens to me that like both my headphones are dead. So yeah, what I was saying was like basically we'll start off by allocating some portion for the size of length of the varchar, and then we'll have the rest of the payload in the rest of the portion. Okay, so yeah, length in bytes is clear. So we have covered how the table layout would look like, and uh, yeah, that's pretty much about the table layout. Okay, so let me go back. Stats manager we have already discussed. It's nothing like basically we don't in this part not implementing any of this functionality, at least not uh, focused on this functionality. So okay, so index manager is another manager class. So we similarly use is new from the file manager, and then based on whether the directory is created or not, we call table definition with the corresponding field. So we need the schema to have index name, table name, field name, and then the corresponding index. Okay. Yeah, we create a table schema called index name, table name, and field name, and then we create a table called index cat with the corresponding schema and the table. Okay, so I think yeah, this is the one that gets created. So index cat, TinyDB, all these four are essentially table files, and this is the index file. All right. Okay. So when we are creating an index, what we do is similar to what we have seen so far. We create a record scan, then we seek to the insert beginning, and then we correspondingly set the index name, table name, and field name. And similarly, when we want to get the index info is just an abstraction for all the index related information. So I think I should, yeah, this should work. Okay, so we iterate through the entire record set, and then we check whether the table name matches with the corresponding table name that's passed, and then we fetch the index names, and we add it to the index info. Yeah, we add the corresponding field name and the index information. All right. Uh, okay. Yeah, that's pretty much clear. And index info, as I told you, it's just an abstraction. So uh, mm, create ID layout. Oh, this is a little confusing. Okay, blocks access is basically used by the stats manager, so that we can ignore, and then records output is also used by the stats manager. We can ignore that as well. Create index layout. I think this part is a little confusing. Schema contains block ID and this thing. Let me just recheck it quickly. Okay, so I got it. So basically here we are again creating a schema for the particular index info. So index info is nothing but table info plus the physical layout and things like that. So we have a table definition newly created. We add the corresponding block and corresponding ID, and then I think these three are the information that you pass as index information or the index layout to the query engine or whatsoever. So block ID and the corresponding data value. Okay. uh, I don't think it's much used, but then yeah, like strange. I, okay, so I was just confused with this part. So yeah, when you create when you open this index info, you basically create a b tree or b plus tree index using the layout and the index name and the corresponding transaction, right? So create index layout is basically used to open that up. So uh, with the create index layout, basically you pass so you are setting the layout to be having three items. One is block ID and the corresponding one is block, and the other one is ID, and uh, the third one is whether based on the field name, which is the corresponding index name, whether it's an integer or a varchar, we check whether it's a add in field or an add string field. So if it's a integer index that you have created, you will use the add in field, and then you will add the field as data value. And if it's a string field, you will create the data value as string and then add it. Okay, so I think I'll need to revisit this part. Not sure completely, but then yeah, let me. For now, let's close this, because on a high level we get an idea of what is catalog. So basically, catalog is responsible for the metadata information of the table and all the columns and offsets and things like that. Okay, so it also comprises of index related information, which will be used for index related queries. All right, so I think that's pretty much it. So we are good to go for now. All right, so I think we have so far covered the front end and the query engine. So later on we'll cover the storage engine, how storage engine is like designed in our TinyDB project, and later on we'll see how the transactions and all the rest of the things work. Okay, all right, see you.